Well, we had some ice.
We had some ice.
We had a fire.
Some fire.
Ice over it. And melted it.
And we melted it. Okay. So.
We used a big amount of fire on a big amount of ice.
Okay. Okay, that's an interesting point because one of the questions on your worksheet was, you know, how is that going to change if you increase the amount of ice? Okay, what happens if you increase the amount of energy? All right. Are you going to get a different curve?
Yes.
How?
Well, it will be
It would take
a
longer.
different shape, but it's the same idea. The same thing's gonna happen, but it's tracing.
Okay. Is it still going to look something like this?
Yeah.
Yes.
Okay. So what would happen if we had more ice?
It just
It would be longer.
Okay, it would just kind of elongate. So it would take longer to melt this. It would take longer to heat it up. It would take longer to evaporate it.
What are we supposed to write that down?
I'm not terribly worried about that so much. Kind of be aware that what would happen if you increase the heat that you added?
It would shorten.
Okay, so would it take as long to melt it?
No.
No. So this would be a little bit shorter. This would probably be a little bit shorter. A little bit shorter. So you get the same shape, general shape, but the lengths of those shapes change. Okay, so we can account for the fact that some of us had more ice, some of us had more heat. Okay, it just changed a little bit.
Do you have any recycling that you're taking?
It would be in here.
This is really screwed up this video.
That's okay. They'll just let me know. It'll be good. All right. So what was happening here in our ice?
Was melting.
Starting
So
to
it's a phase.
And
All right. So we had here is where we had our solid. And where did it actually finish melting?
Right at the end of that curve.
Right.
Yeah. Starting curve.
So here's where we have liquid.
liquid.
Okay, it's all liquid.
Yep.
All right, so we started with a solid, we melted it, we ended up with liquid. Now, what do we have in between there?
Phase energy.
Okay, we've got a couple things going on there. Okay, one, we have another color. We have a change in phase energy. I did forget the E.
Phase.
This is right.
Just
Okay.
instantly.
This is what's wrong. Okay, we have a change in phase energy. Make that prettier.
There.
All right, now when we say a change in phase energy, what do we mean?
The state of matter.
Okay.
Not forgetting about the E.
I know, right? The E isn't coming with me today. So we have a change in phase energy. What does that mean?
So we are changing
It goes
states
from
of matter.
solid
The E. What is wrong with the E?
What are you talking about?
She keeps forgetting all the E's. I thank God she forgot the E.
I declare today no E day. Okay. Okay, we're changing the state of matter. All right, now in this case, what is our change in state of matter? What are we actually doing there?
We're turning a solid into a liquid.
All right, and what is that called?
Melting.
We are melting.
Yeah, I guess. I was trying to think of those particles that they were.
All right, so if we melt
Melt.
something, what are we doing?
Increasing the speed of the particles.
Are we?
Or no,
Because what is going on right here? What is temperature?
Energy. Speed of the particles.
The speed of the particles. So if we talk about this as the speed of our particles, if that's how we define temperature, this is a graph, remember. So down here somewhere we have 0. Up here,
Big
about
number.
here, we have 100. Okay, so this is measuring the speed of those particles. What's the speed right here? 0. What's the speed right here? 0. What's the speed right here? What's the speed right here? Okay, so
Oh,
one.
slightly
So-
about 0.2.
Having enough problems today. Okay, so if you have a flat line on that graph, is the speed of the particles changing?
No.
No. Is the temperature changing?
No.
Is the energy changing?
Yes.
Okay, the energy is changing. In what form?
Phase.
The phase. Okay.
Okay.
We don't see a change in temperature, but does that mean that there's no change in energy? No. All right, so what we have a change in phase. We have a change in the state of matter. We have a change in those particles, but is it the speed of those particles? No. Okay, so when something is melting, what is actually happening?
The energy is
The arrangement of the bonds and particles.
Okay, so we're looking at that specific arrangement. So the definition of melting, if you define this, okay, if we go from a solid to a liquid. Okay, we're going from a solid to a liquid. If we're going to draw a particle diagram of that solid, what would it look like?
Well, so you have a solid figure.
Dense.
Okay.
So where the particles
All right, what do we know about solid
orderly
particles?
form.
We have little tiny particles here. Okay, are they in motion?
Yes.
Yes, they are. And not much, they're just kind of vibrating, so we'll make some little, my picture's too small. So what happens to it?
The bonds break.
The bonds break. So now we have particles that can slide past each other. But I can't necessarily draw. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What is in between here? What's in between there?
Melting.
Phase.
It's melting. What phases of matter do we have in there?
Both of them.
We have both of them. We have a solid and a liquid. So here we have only solid. Here we have only liquid. And it doesn't just suddenly, there it is. Okay. You've got ice and, you've got solid water and liquid water in that middle part. What do we call it when we go from a liquid to a solid?
Freezing.
It's freezing. Okay, so if we freeze something, we're going from a liquid to a solid. Okay.
I feel like that's pretty common sense.
Good.
I mean, freezing.
We are-
What would the graph look like for freezing?
Backwards of that,
How would you tell if it's backwards?
you would have
In-
the, it
You
would
should have to
like,
flip the
it would be
entire thing
hotter.
up.
It would be a cooling curve.
Yeah, that's what
Instead
I
of
mean.
a heating.
Okay. I need another color. Actually, this is the highlighting color might be different. So if you have a cooling curve, what's happening? Where are we starting? Okay, we're starting with a gas. If we cool something, what's going to happen to the energy? It's going to go down. So we're going to take energy out of it. So here we've got this.
Oh, yes.
That's an awesome mark.
It's an X.
It's actually not such a bad drawing. Okay. So up here, we've got gas, liquid. So what happens at this point?
It's a liquid.
A phase, a change in phase energy happens. Starts to happen.
It's all liquid. And what is going to happen as we go across?
Change to solid.
It's going to change the solid. So over here, at some point, we have a solid. Okay. So how is our energy different on our graph? Is it still going to be going this way? Are we going to be increasing that way?
No, yeah.
Our energy will actually be going this way. So what this means is our energy as we go this way gets smaller. Okay, the purple one that lines up with this purple line. Okay, so this purple line is increasing energy. So as we increase energy, our curve will look like this. As we decrease our energy, so here's our arrow. Okay, as we decrease our energy, our curve will look like this. What would we call that? A cooling curve. Okay, so we've got cooling curves. Can you see that at all? I do like the yellow. And we have heating curves. So what can you tell me about the freezing point of a substance and the melting point of a substance? Are they related at all? Yeah. At what temperature are we going to melt that liquid?
Oh, no.
If this is water. Say this is water.
32 degrees. No.
That's
It's the
freezing.
same thing, isn't
At 0 degrees Celsius, right?
it? 0 degrees Celsius.
Okay. When are we going to freeze that water?
0
0 degrees Celsius.
That's right.
Okay. So think about that for a second.
Ah.
That's
I
kind of a
hate
weird
that.
thing.
I hate it so much right now.
The fact that they're the same?
Yes.
Why is that?
Because you think freezing would be colder and heating it up, it would have to be hotter.
Okay. But what is happening if you're freezing that water? What are you doing to it?
You're making it into an ice.
Okay, you're making it into ice. You're making it into a solid. So you're going from a liquid to a solid. So what are we doing to the particles there?
Slow them down.
We're slowing them down. So we're slowing them down to a point where those bonds can be created. Okay, so we can stick those things together with those solids. What are we doing when we melt something?
Breaking.
We're breaking them apart. So would it make sense that at the point where we can break those things apart, they would also be able to form if you went the other way?
Yeah.
I feel like you're staring
Trey.
at me. I don't
Well, you seem to have a
understand.
really hard time with this. It's like, I think we may have lost Trey. Okay, so the freezing point and the melting point, these occur at the same temperature. They occur at the same point on our graph. Okay. So what kind of a change in energy is this? It's a phase energy change. It's the same thing. It's a phase energy change. Oh my god.
Again.
Today's not your
There
day.
you go.
I don't know what he is killing me today. Okay, what is the difference between this change in energy and this change in energy?
You're adding and losing
Okay.
energy.
One, you are adding energy.
You're subtracting energy.
One, you're losing energy. You're subtracting that energy. Okay. If you have 100 grams of water, I will make this up for now. You have a certain amount of energy that you have to add to melt all that water. If you have 100 grams of water, how much energy do you think you're going to have to take away to make that a solid?
The same amount.
The same amount. So these two things are equal. So the phase energy to melt something will be the same as the phase energy to freeze something, just in the opposite direction.
Cool.
Okay. Make sense?
Yep.
Alrighty. Now, what is happening? Bother me. What is happening? How many colors I can get here? What happens here in our lab? What happened right there?
It's
Going to.
it started another
Starting to
change in phase
Go
energy.
to a yes.
Okay, starting to go to a gas. So we have all liquid here still.
Liquid.
But what is starting to happen? Let's just say here.
It's forming to a gas.
Okay. If we go all along this way, it'll become a gas. Okay. So what kind of energy change is that?
An increase in phase.
Okay, it is an increase, I got it, in phase energy. My delta looks funky, but I got the E. Okay, so we're increasing our phase energy. What do we call that when we go from a liquid to a gas? What's the term for
Boil.
that? We boil it. What's the term for that actual
Evaporate.
evaporation?
Almost had it.
Okay, so evaporate, we're going to go from a liquid to a gas. What are our particles going to look like there?
Random motion.
Okay, we're in a liquid. I probably need bigger pens on my rooms. We're moving here. And it's going to end up, we'll make little comment things here. Like that.
I feel like it's like bunny ears.
Look, it's jellyfish that are floating around.
Random.
I watched
fields. What are you gonna get in between? What do you have in between?
Both.
You have both. Okay. So when you draw a particle diagram in between, you're gonna have some that are up here.
Under the two. Just
Okay. And actually, in the solid and the liquid, how is that gonna look in the middle? This is a little harder to draw, especially in the tiny box that I have.
There's gonna be some that are just wiggling and some that are bouncing around.
Yeah, there's some that are bouncing around. There's some that are just wiggling. Sounds a little harder to show.
Yeah.
What happens? What do we have here in our diagram, in our graph?
Yes.
Okay, here we have gas. What starts to happen here?
Liquid.
It becomes a liquid. This is where it's all liquid. What is that called?
Condensing.
Condensing. Okay, so if you condense, we go from a gas to a liquid.
How hard is that to do?
Hmm?
How hard is that to do? To condense a gas into a liquid.
You just have to, what would you have to do to it? What happens here?
Heat it up. Cool it.
You have to
Well,
cool it,
away.
but you would have to have a really dense. You have to have a lot of it.
Well, okay, so if you have,
Well, it's just like a water bottle.
right,
With condensation.
right. To get a lot of condensation, yes, you would have to bring all that gas in and do that. I think I understand what you're saying there.
Yeah.
Like if you were to try and fill up that bottle with water, from gas from the air, that would take a lot. Yeah, you would have to bring in a lot of gas.
Oh, I do that all the time.
That's,
Really easy.
that's how I get my water.
Mm-hmm.
So what kind of change is going on right here?
Negative.
Okay, this is a negative. We're taking energy away. Taking that phase energy away. Okay. Now, can you go from a solid to a gas?
Yeah.
You can. What is that called?
Sublimation.
That is called sublimation.
Ooh.
Nice.
Fancy. Ooh.
This is where you have a solid. You go directly to a gas.
Dry ice.
Dry ice is a very good example of that. Dry ice is frozen carbon dioxide. Okay, so it's not ice what you normally think of. It's not water ice. It's carbon dioxide ice.
Don't eat it.
Don't eat it. You really don't want to even touch it.
Yeah.
For
Oh, really?
Yeah, it's really good.
really.
I eat it all the time.
They don't like
Breakfast.
it. I put it in myself.
Should have gotten some today. If you take dry ice, you can get it at the grocery store. They have it at the grocery store. If you take frozen carbon dioxide and you set it on the counter, it doesn't become a liquid. It doesn't melt and then evaporate.
It immediately evaporates.
It immediately sublimates. It immediately
Ah.
becomes a gas.
Nah.
Why is that?
That's different.
That's how it reacts
Why
to
is that?
oxygen.
Well, it's not reacting to oxygen because it's still carbon dioxide.
Because
It's still
so
releasing
cold.
carbon dioxide gas.
It has something to
Because it's boiling point, it's freezing point.
It is so cold that it has to be.
They're not the same, but they're really, really low. Okay.
Yeah.
So when we talk about the freezing point of carbon dioxide and we talk about the evaporation point of carbon dioxide, the evaporation point of carbon dioxide is really low. I don't know off the top of my head what it is. But at room temperature, that's when it evaporates. And if it's a solid, it's not going to melt and then evaporate. It's just going to skip that step. Okay, the energy comes in so fast that it's just going to skip that step. Can you go the other way? Can you go from a gas to a solid?
Yeah.
Yeah.
What is that called?
Deposition.
What is it called?
Deposition.
Deposition.
It is deposition.
This is new to me.
He is on it today.
I thought we learned it in like seventh grade.
I don't remember.
What's an example of deposition?
No clue.
The stuff on your windows that I can't think of the name of.
The frost.
Yeah, frost.
Frost. Okay, a lot of people think that frost is like frozen dew, and it's not. Okay, what's happening is you have that water vapor that's in the air. It's always in the air. And if it gets cold enough, okay, if the temperatures get down below freezing fast enough, that water vapor just freezes to whatever it
Bubbles.
touches.
Sort of. But
Yeah,
it was
there
from
was
a
that
gas
on
instead
the
of
bus
liquid.
last night.
Like what?
That was just a visual.
Okay.
Like just a thought in my head and
Okay.
it came out of my mouth.
Okay, so frost. Frost is an example of that. So why does it frost sometimes on your windshield but nowhere else?
What?
Why would it frost sometimes on your windshield but
Because
not necessarily on the grass or anywhere else?
Because the ground can't
Because the
heat.
inside of your cars.
Yay!
Yeah, there's a lot more heat energy in the ground than there might be like on concrete or in your windshield. Okay, so you get that a lot. Okay, so those are your phase changes. Okay, those are the different ways that we can change that phase energy. Now, is there a way that we can quantify that?
I imagine so.
There is, yeah. What do you think we would have to know?
We would have to know.
Hey, you got to eat.
In order, so we've got our thing of ice sitting here. We want to know how much energy it's going to take to melt all of that ice. What do you think we're going to need to know?
The melting point.
Of one ice cube.
Well, would it matter what the melting point actually is? Can we melt that ice without knowing what the melting point is? Okay. So temperature is really not important. We've talked about one of those things. What if you have 100 grams of ice? Is it going to take a certain amount of energy?
Yes.
Yeah. What if you have 1,000 grams of ice? How's that energy going to change? Is mass going to be important there?
Yes.
So one of the things that's important is the mass. Okay, mass is important. When we want to melt something, it's going to be a big deal. There's still snow in some places.
There's a big pile of snow out behind the wrestling room.
Is there one still out there? Okay, it's been, what, a couple weeks now since we've had snow.
Underneath my trees in my yard, there's snow underneath it still.
Okay, some of that is it getting energy to begin with. But some of that, why is there a big pile outside the wrestling room?
There's no like it. So.
Well, there's a couple areas back there. One, and this I try to avoid it because I about drove into the weight room last year. It's shaded off from all sun. There's not a whole lot of airflow back there, so there's not a whole lot of energy. There's not a whole lot of energy transfer to it, so it takes longer to change state.
There's an awful lot of energy. There's not a lot of energy back there. There's also, where did they put all the snow when they cleaned out the parking lot?
They piled it up right there.
They piled it outside the wrestling room.
It's all in one big pile.
Okay, so what's another reason that there's probably still ice there?
There's a lot of it.
So much of it.
There's a lot of it there. Okay, so mass is important. Now, can you think of any other thing that maybe might affect what would melt it?
The substance itself, like what it is.
What if that was, totally drawing a blank on what that might be. The only thing coming to my mind is Jell-O. What if you had a big pile of Jell-O sitting there next
Why would
next to your water? I don't know why. That's what was popping into my head. I'm not-
300 pounds
she
of
really
Jell-O.
wants Jello?
Let's go with iron.
That would take a lot.
Okay.
Just take your spoon out there and have some lunch. For the next 3 weeks.
Okay. That's relaxed. All right, so we have this big pile of snow. We'll go with iron because you don't seem to like the Jell-O example, right? Is it going to take a lot more energy to melt the iron?
Yes.
Yeah.
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 Okay, so when we talk about changing the state of matter, it does depend on the substance. What are we going to have to do to that iron to make it melt?
Heat it up.
Heat it up a
High
lot.
energy.
Okay, an awful lot. So the substance is important, and the mass is important. Anything else?
Substance would. I know there's like so much more to this than what we're talking about.
There's really not.
Really? Is it?
Really.
It seems like there should
This
be
is
though.
it.
Oh.
This is actually it. When you talk about phase energy and you talk about how much energy it takes to change the state of matter, either from solid to a liquid, a gas to a liquid, a solid to a gas, whatever it is, the amount of energy, and this is what we're talking about here, the amount of energy that it takes to change the state of matter depends on the mass of the substance and some heat constant. Okay. That's what it depends on, just that. Just those, it is pretty simple. Those two things. So if we're melting ice water. Water, ice. We're melting wine. We're melting ice. Okay, we need to know how much energy does it take to melt 1 gram of ice?
So the reason that the melting, freezing, evaporation point, the reason that doesn't matter is because those are given for the substance they work in.
These have been determined.
Okay.
These are constants. When we say a heat constant, what we're talking about, we've measured that. We know that it takes a certain amount of energy to melt 1 gram of ice. At the top of your paper, where it says heat constants, energy constants, actually is what it says.
Yeah.
Okay. There are a couple there. Actually, there's 4. All right, if you look at the first one, it says heat of fusion. If you fuse something, what do you do?
You combine it.
Put it combined it together.
Yeah, it's coming together. You're fusing it, you're sticking it together. So what do you think that describes?
It describes fusing something with heat.
Or, in the
Or-
case of changing states of matter, what do you think that describes?
Energy and the
The chemical
and the
Temperature?
particles in the substance.
Okay.
Huh?
So if we go from a solid to, if we go from a liquid to a solid, let's do this one. If we go from a liquid to a solid, what are we doing to those particles?
Putting it
Slowing them down.
And what do they end up doing to each other?
Energy.
touching.
They bond.
They're bonding. They're sticking together. They're fusing together. Okay. So we don't have to weld them together. The particles can stick together. So heat of fusion. If we are melting or freezing, the amount of energy that it takes to melt 1 gram of ice is 334 joules.
Joules.
Joules. Now what is a joule?
I have no clue.
It's the amount of
1,000.
energy.
If you had to guess, what would you say a joule is?
Same for a joule.
Yeah, it's an amount of energy. Okay. This is what we measure energy in. Guess who it's named after? Joule.
Oh,
Mr. Joule.
yeah, it's,
Okay.
yeah.
Okay.
Joule J.
That name.
Joule is just an amount of energy. It's what we measure energy. It's like when you say this has a mass of 7 kilograms. Kilograms is a way to measure mass. Joule is just a way to measure energy.
I thought it was watt. Wait, no, that's.
It's another scale that we use.
Now, what happens if we're going from a liquid to a gas? There's another constant on there. What is that other constant?
The heat of vaporization.
The heat of vaporization.
So it's saying
You can vaporize something. What do you do? Yeah.
So the, how do I?
You turn it into gas.
Cool.
Okay, vapor means gas. So if you evaporate something, or if you condense something, you will use the heat of vaporization. Okay. Now what do you notice about the number given for the heat of vaporization of water compared to the heat of vaporization, or heat of fusion of water? It's a lot higher. Like almost 10 times higher. So what does that tell you about the amount of energy to go from a liquid to a gas compared to a solid to a liquid?
It takes a lot more.
It takes a lot more. It's a lot easier to melt something than it is to evaporate it. And it takes a lot less energy.
How? Has anybody ever successfully evaporated iron or like steel or any sort of metal?
I don't know. I suppose maybe I don't know what the
Really?
evaporation
That'd be
rate
really
is, to be
dangerous,
honest.
like gas metal.
I wonder.
metal.
you should try
I
that.
don't
Probably
think I would
somewhere
wanna
we
breathe
haven't
that
seen
in.
that.
I don't think I would
That
wanna
is
breathe
mean.
that in.
You don't want to
Get
breathe
your
that.
lungs in.
Kristen,
It's
you like
hard,
that?
it's like-
Right here, look at me, and you're looking at it.
Okay.
I don't know. I would have to look that up. So if we want to know, here's the key idea here. If we want to know how much energy it takes to melt or freeze something, we need to know the heat of fusion and the mass. So this can be either heat of fusion or heat of vaporization, whichever one it is. You have to identify what that change in state is. Okay, so you can't just start plugging in numbers. You have to identify it. So if you evaporate or condense, it's the heat of vaporization. Okay, so the constant that you use depends on which change in state you have. Make sense? Yes.
What
We're
are
not
sig
gonna worry about sublimation and deposition. Actually, essentially what you do is you add those two together, and that's how much energy.
What are sig figs?
Significant figures, we're gonna talk a little bit about rounding when we do this. Because that'll be important.
I was wondering if that was a typo.
I read the
We're gonna hit that again. All right, questions about changes in state.
Do we have to do this work? Right here.
We're not done yet, but yes, we will.
Should I stop it?
All right, changes in state depend on mass and that heat constant. Okay? Now, do we only have changes in state?
No.
No, what else do we have? Okay, what's going on here? This part right here, what happens?
Speed of particles increase.
The speed of the particles are increasing. Even if you hadn't done this lab, how would you know that? Because it's in a graph, right? What is graphed on this axis?
The speed.
The speed, the temperature. And what happens to the speed and the temperature of those particles? It goes up. Okay. So even if you hadn't done this lab, you would be able to read that from the graph. All right, so what kind of energy change do we have there? What do we call that? Thermal energy change. Okay. So thermal energy change refers to what? Change in temperature.
Look at style man.
Okay.
I just lost my.
What kind of thermal energy change do we have here?
Positive.
This is positive. What kind would we have here?
Oh my god.
Okay.
Drop this pencil.
How do we know this is a negative thermal energy change?
That's the speed decrease.
Now the speed is going down. And if we follow this graph, this is a negative slope. So that's a negative change in energy. We kind of touched on this a little bit before. Can you have a colder substance than zero? If this is water, can you have something below the freezing point of that substance? Okay, so here we could have a thermal energy change as well. What happens if you evaporate all this gas and you keep adding energy to it? What's going to happen to that gas?
It's gonna increase speed.
Yeah. So we can get a graph, and this is what your quiz looked like yesterday. This is what threw some people off. We can have an increase in temperature, change in phase, increase in temperature, change in phase, increase in temperature. Okay. Now what do you think the change in thermal energy is going to depend on? Up here it depended on mass and the substance. What do you think the thermal energy change is going to depend on?
The type of day it is. If it's a nice day,
What?
it's probably gonna be hot.
Okay. Well, but that's what we're kind of trying to find, right? Okay, that amount of energy.
Can you evaporate water if it's like super cold?
Can you sublimate
Like in the
water?
freezer?
Huh?
Like in the freezer?
Yeah, like you know how people take boiling water and then throw outside and it like evaporates.
We
Like,
actually
freezer,
could have done
that's
that, yeah. We did that on
Oh, I
the
did
snow
that.
day.
I have a video of it.
Yeah.
It's cool. No, I took it in slow motion, so it's really cool.
That's awesome.
Throw it at somebody.
What if you have a cup of water that you're heating up? How's that going to compare to a pot of water that you're going to boil? Which one's going to take more energy?
Pot,
Why?
because it's bigger.
Okay, has more mass, right? So is mass going to determine how much energy it's going to take to change the temperature?
Yeah.
Okay. What else?
The substance.
The substance. If you heat up water, as opposed to heating up iron,
It's gonna be a little easier to heat up water.
Is it?
Well, it depends.
say you have a cup of water sitting on a fire, and you have a cup of iron sitting on a fire. Which one would you be more likely to want to touch?
Cup of water.
Why?
Because the iron can hold more
Okay.
energy.
The iron is going to change its temperature a lot faster than the water. Okay, so the substance will be important. We actually call this has an abbreviation of C. This is the specific heat, or the heat capacity of something. Let's put that here. Okay, the specific heat. And again, this is a constant for everything. Think about the lake. In June, first part of June, summertime, it's really warm, and everyone thinks, let's go swimming.
No.
No,
Why not?
actually,
It's still really cold.
The lake has not warmed up. Why?
because all of that water,
Because
so
of
much of it holds.
All of that water. Water actually has a really high specific heat. If you look on here, it has 4.18 joules per gram degree Celsius. So if you want to take the lake, think about how many grams of water there's probably in that lake.
A lot.
A lot.
It's a lot.
Inconceivable.
A lot of grams in there. To take all of those grams of water and raise it 1 degree Celsius.
That'd be huge too.
That's a
going to
lot
take-
of energy.
It's a lot of energy.
Ridiculous.
Okay.
I'll do it when I jump in the water.
It's amazing it ever warms up at all, right? Okay, so when we talk about the specific heat, what we're actually talking about, to take 1 gram of a substance and raise the temperature 1 degree Celsius. The amount of energy that it takes to take 1 gram of water and raise it 1 degree Celsius. Now, if you look at water, what is the specific heat for water?
See, didn't we just go over this?
4.18. So it takes 4.18. If you have 1 gram of water, 1 milliliter of water. Think how small a milliliter is. Really small. If you want to raise that 1 degree Celsius, it takes 4.18 joules of energy. That's really high. Water has a very high specific heat. Okay, that's really not very common at all. Which kind of gives us a clue to the next part. How much energy? What else do we need to know? What if we want to take the lake water and raise it 10 degrees? Is that going to take more energy?
Oh yeah.
What if we want to raise it 20 degrees? Is that going to take more? Okay, so the change in temperature is also important.
This is a lot of remembering for one day.
Yeah.
Well, most of this you already know.
Ish.
This is new.
Kind of.
Kind of. Kind of. But you have to think about it. So when we look at the total amount of energy, a lot of color on here. We look at this total amount of energy to start here. We've got ice, say -8 degrees Celsius. What do we have to do to be able to melt it?
Heat it up.
We have to heat up. We have to heat up the temperature. What's that going to depend on?
Change in thermal energy.
Change in thermal energy, okay, which is the mass, the specific heat, the change in temperature. Okay, then we have to add energy into it to melt it all. What's that going to depend on?
Change in energy.
Okay, the heat of fusion and the mass. And then we're going to heat it up to boiling. What's that going to depend on?
Thermal energy.
The thermal energy again. So the mass, the specific heat, the change in temperature. Now, if you look on your sheet, what do you notice about specific heat capacities on here? How many are there for water?
Two.
There are 2. Why are there 2?
There's a solid and a liquid.
Okay. This also depends on the state of matter that it is in.
Why?
To increase the temperature of solid water, the specific heat capacity, 2.1 joules per gram degree Celsius. So it takes less energy to heat up ice than it does to heat up liquid water. Okay? So when you're looking at this, you need to be very specific. Do we have solid water? Do we have liquid water? Are we melting it? Are we evaporating it? Are we freezing it? Okay, so we're looking at how much energy does it take in each part of that graph. Okay,
Yeah.
questions yet? Yet.
Too many.
So you want to try it?
How do we go over the joules per gram Celsius thing again?
Your specific heat? The specific heat is a constant. Okay, so we have measured this for water. So if we have 1 gram of water and we want to raise that temperature 1 degree Celsius,
How many joules?
it takes 4.18 joules. It takes a certain amount of energy. Now, if we had 1 gram of iron and we want to raise that gram of iron 1 degree Celsius, it's going to take a lot less energy. Something like 0.3, I think. It's not very much at all. It's very, very little. So this is, when we say specific, what do we mean? What does that refer to, do you think?
Like it has to be that amount?
Not that amount, but that substance. It's very specific for that substance. So iron has a specific amount of energy that requires it to raise the temperature.
Is that why they
Are the joules per like gram Celsius? Is there anything higher than water?
I want to say no, but there might be something that I'm missing. Water is really, really high. Has a very high specific heat. You know, we talk about what we
Why would it be so high?
has to do with the bonds. We remember when we looked at the water, we saw it was really polar and it sticks together. It's really hard to get those to change because of that polarity, because of the bonds between those hydrogen bonds.
I don't get why we would take more heat though to melt.
to evaporate liquid than it would
Yeah.
to melt a solid. Like
Well, in order for a gas form, gases just in general have a higher energy just because of that state of matter. When we did those bar charts, remember we assigned those 4 bars of energy?
Yeah.
Because gases just have a lot higher energy. They just do. So to break apart and actually really truly break apart, when you go from a solid to a liquid, you're just kind of, you're breaking them apart, but they're still together, they're still sliding together. In order to actually evaporate them, they've really got to break apart
so
and break free.
typically if you're working with pretty basic instruments, your middle change in thermal energy is going to be the longest change in your graph of energy, won't it?
Probably. Yes. I would say yes on that.
I mean,
Or,
as long as
well,
you're heating at a constant rate. or
actually
changing it.
this would not be, probably this to this. This would be a lot longer than what I have drawn here. It would actually be, because it takes a longer time, it takes more energy to do that. So if you're adding it at a constant energy, this would be quite a bit longer than that. I did not draw that to scale at all. I probably should.
What's the amount of joules? Like, what's that? The symbol, like the amount of energy. Like, like on number 1, it says how much energy does it release to the surroundings. Is that? Would you measure that by like the amount of joules?
Yes. Yes. Right. So if we, okay, we'll do number 1 here in a second. Everybody got this?
Yeah.
Anybody want to take a picture of this?
Yes.
Okay.
Actually, can somebody take a picture of that and send it to me?
Has anyone seen
Should I stop it?
Yeah.